Hi everyone, thank you for tuning in. In this video, we will discuss explaining the predictions of neural networks. The black box behavior of neural network models raises the question, which input features contribute to their output? Identifying the contribution of features to the output of the neural network is known as feature attribution. Feature attribution is the focus of this work. Recently, the predictive information of features is proposed as a proxy for the measure of contribution of features. And in this work, we propose a method to identify the predictive information of input features. The method has the advantage that it results in fine-grained identification of input features information. In other words, the attribution is of high resolution. The method is also agnostic to network architecture. So far, the predictive information is only identified for latent features. By placing an information bottleneck within the network, we propose a method to identify input features with predictive information directly in the input domain. The core idea of our method is leveraging a bottleneck on the input that only lets input features associated with predictive latent features pass through. We will illustrate the idea shortly, but before that, let's briefly go over the background work, IBA. The information bottleneck attribution, or IBA, explains the prediction via measuring the predictive information of latent features. This is achieved by placing an information bottleneck on latent features. IBA places a bottleneck on features of an intermediate layer by injecting noise to the features. The noise-injected features coming out from the bottleneck are referred to as bottleneck variable Z. The bottleneck is thus optimized such that the mutual information between the features R and bottleneck variable Z is reduced, while the mutual information between the bottleneck variable Z and the target output Y is maximized. In other words, the method aims to remove as many features as possible by adding noise to them while keeping the target output. The remaining features thus have predictive information. The main challenge with computing the mutual information between feature maps R and bottleneck variable Z is that the distribution of Z is not tractable. Therefore, IBA methodology resorts to variational approximation and approximates bottleneck variable Z with a Gaussian distribution. IBA method has two inherent approximations which cause problems. First, in order to accomplish feature attribution for the input features, IBA method limits itself to convolutional architectures. It first finds the informative features of a hidden layer, then interpolates these values to the input dimension. From the perspective of this approximation, it is desirable to apply IBA to early layers to mitigate the effect of interpolation. The other approximation is the Gaussian approximation of bottleneck variable. The Gaussian approximation is reasonable for deeper layers of the network. However, as we move toward the input, the assumption leads to an overestimation of mutual information between feature maps before and after the bottleneck. Here we observe the result of using such a Gaussian approximation for various layers of a neural network. As the overestimation of mutual information increases by moving towards the early layers, the IBA optimization removes more features with noise. We can see that the predictive feature, the broom, disappears as we move IBA towards the early layers. The approximation of distribution of Z is most accurate when IBA is applied on the deepest hidden layer. On the right, we see a preview of the result of our proposed solution, input IBA. We aim to come up with a more reasonable choice for the approximation of the bottleneck variable, such that it is applicable for the input. We compute the mutual information directly in the input space and avoid the approximation issues inherent in IBA. We take advantage of Gaussian distribution approximation of bottleneck variable being reasonable for deep layers. Thus, we first find the bottleneck variable Z star that corresponds to the predictive deep features by solving the IBA optimization problem on a hidden layer. The bottleneck Z star restricts the flow of information through the network and keeps deep features with predictive information. Then we search for a bottleneck variable ZG on the input that corresponds to bottleneck variable Z star. This translates to finding a mask on the input features that admits input features which correspond to informative deep features. The final goal is keeping only predictive features of input. Therefore, the input bottleneck ZG can be used as a prior knowledge for the distribution of input variable ZI. We then proceed and solve the optimization problem by solving ZG as a prior for ZI. We refer to this methodology as input IBA. Now we get into details of finding the input variable ZG. We search for an input variable that minimizes the distance between the distribution of latent variable Z star and the distribution of the hidden representations when the input bottleneck ZG is applied. In this work, we use Wasserstein distance, and we employ a generative adversarial scheme to minimize the distance. The parameters of the variable ZG are the learnable parameters of our generative model. We sample from the input bottleneck variable ZG and feed it to the network to generate the hidden representation. The discriminator serves to discriminate samples from the output of the generator and the distribution of Z star. The result of the generative adversarial optimization is the prior bottleneck ZG. Now let's see the model in action. We observe that the results of different attribution methods are substantially dissimilar for the same prediction. This is a caveat for the community that the attribution problem is far from solved. There is a consensus between GradCam IBA and input IBA in these examples. Later on, we see that the feature importance evaluations show that these methods indeed reveal important features. Our method, DeepShap, and integrated gradients are fine-grained. However, we observe in feature-important experiments later on that only input IBA is attributing to input features among fine-grained methods. In this slide, we see the result for the NLP task on the IMDb dataset. We see that IBA does not translate to RNN architectures when attributing to input tokens, and we observe that our method and Lime attribute to relevant tokens. We also perform parameter randomization sanity check. The experiments evaluate whether the attribution changes after randomizing the parameters of the neural network. The randomization starts from the final layer and moves towards the image. We observe that the attribution is randomized after parameters are randomized. We also evaluate our method with several human-agnostic feature evaluation metrics. These metrics are crucial as they objectively evaluate whether the attribution method is identifying contributing features. We evaluate our method and other attribution methods with sensitivity N, insertion deletion, and remove and retrain evaluation metrics. Finally, we propose a new human-based evaluation metric. Human-based evaluations evaluate how visually interpretable the results are. Note that they do not evaluate whether the methods are correctly identifying contributing features. This is only an evaluation for visual interpretability, or also fine-grainedness. We intend to quantify the visual alignment between attribution maps and ground truth bounding boxes. Previously in the pointing game bounding box evaluation, the proportion of top-end scored pixels located within the bounding box is computed. Pointing game method only considers the ranks of the pixels, but ignores the distribution of attribution values outside the bounding box. An example of the limitation of pointing game is visualized here. We propose effective heat ratios metric, or EHR, to alleviate this problem. EHR varies the number of pixels under investigation to consider the distribution of attribution values. EHR considers multiple quantile thresholds from 0 to 1. At each quantile threshold, the sum of attribution within the bounding box divided by the total number of pixels above this threshold is defined as the effective heat ratio. Finally, the AUC of the ratios over the quantiles is computed. In summary, we propose the new feature attribution approach, that is input IBA. Input IBA avoids several approximations of IBA and identifies the predictive information directly in the input domain. Therefore, input IBA does fine-grained identification of informative features and is agnostic to network architecture. We also propose a new evaluation metric, which we refer to as effective heat ratios. Thank you for your attention.